All right. We're going to go over homework problems for the weekend, which are intended to help prepare you for the test. So the first problem, got a straight line with axis intercepts. I'm going to tell you a couple of things about this, just because they might be useful. Okay. Straight line with axis intercepts, 3, 0, and 0, 1. In the first place, and you should know this because it can be handy. Actually, I'm not going to be in the test yet. There's an extra step in there I don't want to take the time. Okay, so what we have is 2 points. So you got y equals mx plus b. Find m, preferably using a fundamental triangle because you learn something by doing that every time you do it. And substitute the coordinates of one of the points. Okay, so what do we do? Slope. So here's your line. And we can do a fundamental triangle just for these 2 points. Run is 3. The rise is -1. If we go from this point to this point, we have to go down 1 and over 3. So we go negative in the y direction, positive in the x direction. So we're going to have a negative slope, which is obvious. So we can write the slope as 1/3. Remember, that's how we label a fundamental triangle. Label the run, label the rise, preferably with a calculation, but I didn't do it in this case. And the calculation of the slope. So we see the slope here with a box around it, so we don't mistake this -1/3 for the length of the line. Okay, so we have that. Now, let's make sure everything's visible. I think it is, yeah. The slope is -1/3, so y equals -1/3 x plus b. So we substitute. I'm trying to keep as much, trying to use as much, trying to minimize the board space I'm using because I might want to refer to some of these when we get into the 161 class. So if you want to move closer, if you're having trouble seeing it, you're welcome to do that. Anyhow, y equals 1 when x equals 0. So we get 1 equals -1/3 of 0 plus b. And we solve that for b and we get b equals 1. So our equation is y equals mx plus b equals, we write it y equals -1/3 x plus 1. And we can check that. If we plug in x equals 3, we get negative 1/3 of 3, which is negative 1, plus 1, which gives us 0. So y would be 0, and that agrees with the coordinates of our x-intercept. Okay, so that could be a pretty straightforward problem. You're given 2 points, you can always do that. Now, there's a formula for the 2 points. If you want to memorize a formula and use it, that's okay. I think this is easier to remember. But if you got a good memory for formulas, that's valid. I think you understand more from this. So that's the way I want to approach it. Okay. Now we've got another one. Linear function f of x, f of negative 5 equals 2, and f of negative 2 equals negative 1. What's that mean? That means if we draw a graph, we go over here to x equals negative 5, y is going to equal 2. Let's label this negative 5. And keeping with what I really like to see is I'm labeling a whole vertical line through this point, x equals 5, and the whole horizontal line here, y equals 2. And then we have f of negative 2, and up negative 5 is here, negative 2 should be a little bit more to the left. So this is x equals negative 2, and y equals negative 1. So we have this point and this point on the graph. Uh-oh, there's a bad number in there. Okay. I set up my randomizer and apparently didn't set it up in such a way that it says find f of negative 2, but you already know it. Okay, so just by coincidence, I think that's the wrong number here. So I want to find f of negative. Actually, I want to find f of 2. And your solution of f of x equals negative 8. Okay, so here's the graph. The equation. Well, I don't want to take too much time with this, but I'm not going to do a lot of explanation. I'm just doing a fundamental triangle. And I see the rise is negative 3. And the run is 3. So the slope equals 1. Same way I found it over here. And that should be something that's second nature to you. Find the slope between 2 points, label your triangle. And over here, I should have used arrows to indicate a path from this point to this point, so we keep the positives and negatives straight. So the slope is, they're going to keep the positives and negatives straight. Slope is negative 1. And then y is 2 when x equals negative 5. So we have y equals mx plus b. Y equals negative 1x plus b. And then using the coordinates of either of these points, we use the coordinates of this point, which are negative 1, negative 2, negative 1. Make sure I got my points right. Okay. I think we get b equals negative 3. Couldn't be, it should be negative 2. Let's see. Yeah, I'm sorry, it's -3. That agrees with the graph. Slope of 1 from here to here. That's a run of 2, should be a rise of -3. We start at -1, get to -3. So that all fits the graph. Now, my point here is, the thing you really want to do is, if you're given this kind of information, f of -5 equals 2, f of -2 equals 1, just in general, you immediately want to put that information in 2 points on a graph. Because once you have 2 points on a graph, you pretty much know what to do to get the straight line. Okay, so we're just translating from the function notation to an y versus x graph and going from there. So we get the coordinates of that point, and now we want to find y then equals -x minus 3. Something is wrong with this. Exclusion isn't correct. Pause the video. We don't waste a lot of. Okay, then. So, okay, so well, of course, y equals f of x. And our graph, maybe it would be good to label y equals f of x here and x here. Just remind ourselves of what everything means. So that now f of 2 equals -2 minus 3 equals -5. And how do we do that? We can replace, here's our f of x equals this, f of 2, we replace x with 2, we get -2 minus 3 equals -5. And then the equation f of x equals -8. Well, we get -x minus 3 equals -8. And we solve. And it's not -5, x equals 5. Does that agree with the picture? Okay, well, if 2 is here, here's x equals 2. Is it reasonable for this line to be y equals -5? And yeah, if this is 2, then the line doesn't quite have the right slope. This looks more like maybe -4, but -5 is reasonable in terms of the graph. If we had gotten f of 2 equals 5, that would have been ridiculous because the graph doesn't intersect the line x equals 2 up here. It's down here. So the graph gives us a reasonable consistency check. And that idea is really important. And then if x equals 5, could y equal -8? I don't have room to draw the x equals 5 line here. It comes down here and intersects the graph here. And yeah, that could well be that y equals -8. So reinforcing the idea that if we got a good picture of the graph, we can always check arithmetic in our algebra. That makes sense? Hopefully. Okay. And if not, look at the video, send me questions. Now, people did pretty well on this. So ride. costs $13 plus $1.25 per mile. Then a couple of ways we could approach this, and I'm debating. But okay, let Y. Equal the cost, let X equal the number of miles. Then you could ask yourself, okay, it might not be necessary to ask yourself, it might be obvious. Okay. How do you get the cost for 10 miles? Well, cost is $13 plus $1.25 per mile. Multiplied by 10 miles. That's how the calculation is done. And of course, you get an answer there. That's going to equal $25.50. Okay, you might do another. What would it be for 20 miles? $13 plus $1.25 times 20 miles. And that's going to be another $12.50. That should be about $38. Okay. You don't have to do these sample calculations. I do these sample calculations just to get my head around the problem. It shows me how the cost is related to the number of miles. Okay. In each case, the cost is $13 plus $1.25 times your number of miles. But the cost is Y and the number of miles is X. So we can say Y equals, and I'll leave off the dollar sign. We could say Y is a cost in dollars. So the dollar sign is implicit. Y equals 13 plus 1.25x. And there's our equation. Now, if we've done a number of these problems, it becomes pretty obvious because we understand, okay, we're going to take number of miles and multiply it by $1.25 and add $13. And that's all this equation is saying. $1.25 times the number of miles plus $13. Okay. Now we want to find how many miles you could travel for $30. Well, X is 30. No, wait, $30, not X. That part of this. Right, but there we go. Okay. $30 is the cost Y. Find the number of miles which is X. So Y equals 13 plus 1.25X. 30 equals 13 plus 1.25X. For X. I'm not going to take the time to write out the details. We'll subtract 13 from both sides. We'll get 17 equals 1.25X. And we get 17 over 1.25, which is 4/5 of 17, which is 1340. Which you would want to check because I did that all in my head. Okay. And it's
1360.
Yeah, I was coming around to that. It's 1360. 68 divided by 5. I just used fractions. That's 5/4. Divided by 5/4 is like multiplying by 4/5. 4 times 17, 68. 68 divided by, well, 68 goes into 65 13 times. 3 left over, 3/5 is 60 cents. Okay, that was a calculation in some line. We're down 40 there. Okay, and then cost for 12 miles. So find the cost Y. It'll be 13 plus 1.25 times 12. And that is 5/4 of 12, which is 15. And it's Y equals, so Y equals 28. $28 miles for $12. All right. Now, I'm not going to break it down quite as far as the previous. But let's do one about housing costs. In year 4, the cost is $150,000. In year 28, cost is $340,000. Okay. It's stated the cost changes linearly. With time. This tells us we have Y equals cost versus X equals time. And that from X, that's a badly written X, there it is. Okay, that's why I wrote Y. And now assume the cost changed linearly. How much would the cost be in year 10? Now there is a way pretty easy way using proportionality or cost per year, $7,000 some dollars, I think. Okay. And people were getting this, but often not using a linear function, but it states clearly that this has to be solved using the linear function because I'm not testing whether you can reason it out. It's an easy problem to reason out, but you're not doing it by pre-calculus, okay? If you do that. So what I recommend is you put the data on a graph. You put year 4 here and year 28 here. And then, and actually 4 should be a little closer. The origin should be 1/7 of that. And if I break that down into eighths, it's like here. So here would be year 4. And let's go ahead and do what I like to see. Put x equals 4 here. Put x equals 28 here. So we have these lines that frame our graph. And so we can see clearly where 4 is and where 28 is. Okay. Then we put our y values, 150,000, 340,000. So I'm going to put 400,000 up here because then I can divide that in 2 and I get 200,000. And divide that in half and I get 100,000. And then divide this interval in half and I get 300,000. And my numbers fit nicely into this picture. And I don't have to be hugely precise. I could be, but if I'm just jotting this down on a piece of paper, I try to get the numbers about right so I can check my results. But an approximate graph, a quickly drawn graph isn't going to give you accurate results, but it's going to give you a plausibility test for your solution. So I would recommend we do this. Anyhow, the cost in the first year is 150,000. Well, what is 150,000? Halfway between 100,000 and 200,000. Okay. And y is 340,000, a little less than halfway. Between 300,000 and 400,000. So here are 2 graph points. And now I can do what I should be doing, be able to do by reflex. I draw myself a path from one point to the other, usually from left to right, because it's easier to keep track of. And I see my run is 28 minus 4, which is 24. My rise is 340K minus 150K, K meaning 1,000, equals then 190,000. So my slope is, and remember, slope is an average rate, okay? And since we have a linear, we can just say rate. Rate is rise over run. Hopefully be able to see this and you know, see it clearly, more or less clearly on the video. But the rise is 190,000 over 24, which approximately equals 7,900. A little high, 4 times 1976. There's only 24. I think 7,900 is a little high. I'm guessing closer to 77 or 7,800, but your calculator, you get the right number. So the slope is 7,700. And here is a really good picture that shows both the line and the calculation of the slope. I can extend this, get the equation of the line. And again, y equals mx plus b, using the second point. I better write out the numbers. 340,000 equals 7,700 x plus 28, using this point. Okay. In other words, y equals 340,000 when x equals 28. So that I need to learn to think before I write things down. X is 28. All right. 70,000 times 28 plus b. So b equals approximately, I'll ballpark this, 3 times that would be 24,000, 240,000. And it's less than that for a couple of good reasons. I say 220,000. So I'm going to say, that makes sense? Yeah, it does. Now, your actual numbers will differ from these if you do it accurately, but there's a function. Now, to use that function to answer the question, using reasoning very similar to what I used earlier, we just plug in 10 for x because x is the year and y is the cost. And that's going to be 77,000 plus 120,000, which is $197,000. Okay, does that make sense? If your 4 is here and your 28 is here, I'm thinking year 10 is about here. If y equals 10, x equals 10, then y would be in the neighborhood of $200,000, and that's real close to the neighborhood of $200,000. Okay. So this point on the graph gives us 200,000. This gives us 197,000. That's closer than we would expect to be from a quickly drawn, hand-drawn graph. Okay. Now, the last year in which this type of house would cost 200,000. We let y equals 200,000. So y would be 200,000 plus 77,000 x plus 120,000. You get 80,000 here, and you get x equals something. Wait a minute, it's for 250,000. And the 200, I wrote down 200, so it's going to be more interesting. Okay, well, for 250,000, we expect that x would be a couple of years more than 10. Okay, so maybe x equals 13. Okay, from an estimate on the graph, I'm not going to write that out in detail. So now we get 130,000 divided by 7,700, which comes out x equals 14. And you want to check that, but approximately ought to be kind of close to 14. Actually 8 and 130. Not sure about that. So, not going to think any harder about it. Okay. Now, the next problem, using transformations of the appropriate toolkit function. construct a graph of y equals g of x. Equals -2 times x minus 2 squared plus 4. This is y equals AF of x minus k. A equal -2, h equals 2, k equals 4. So we start with the toolkit function. No, not very vertical. With the width of it. Okay. Okay. Let's try again, and we're going to shift. Yeah, right. I'm still not getting a straight line on it. Okay, there's x, there's y. We draw our toolkit function. Here's x equals -2. Here's x equals 2. Here's y equals 4. And we construct our toolkit graph. Not going to draw the construction lines, we'll do that. Okay. Then what are our transformations? Well, we horizontally shift 2 units. Okay, so we go horizontally 2 units, meaning we move our red dot over 2 units. You were like, and now we have x equals 4 equals 2 here, but that is exactly where the dot is going to go in this case. So our red dot's going to go here. And oh no, okay, well, that's what would happen if we didn't have to apply the A. We have to vertically stretch this graph 2 units and flip it over the x-axis. Well, okay, that gives us a graph that goes down to y equals -8. Because, of course, we vertically stretch this box by factor 2. Okay. And that should have been green. My color coding's all messed up. Okay. Well, live with it. Here's our toolkit graph, y equals x squared. This blue graph is y equals -2 x squared. Then okay, want to get rid of this construction. We'll get rid of that too. The graph looks more accurate. Okay. Now we've got to horizontally shift 2 units. What to use here. So I'm going to have to shift this graph over so the red dot is here. It's this graph, the y equals -2 x squared graph, that I have to shift over. And my rectangle for that graph will be here. And it's going to look like this. And then we have to shift up 4 units because our vertical shift is 4. So finally, this red dot is going to shift up to here. The box that we need is going to be 4 units higher in the box we have down here. So right here is our final graph. Graph that we have here in orange was y equals -2 times x minus 2 squared. It was shifted. We had the -2x squared graph shifted right 2 units. X got replaced by x minus 2. There's our new graph. Then we shift up 4 units, and this whole rectangle here shifts up to here. There it is. And we'll label the line y equals -4. We shifted y equals -8 up 4 units to y equals -4. And there's our final graph. So what we've done, if we just kind of track the red dot shifts from here to here. And then from here to here. And hopefully that helps follow. Okay. Now, what else did I ask? Without using the formula, use algebra to solve the equation g of x equals 7. We got a question. Okay, had a good question. What do you do if you don't have all these different colors available to you on the test? And you won't, I mean, you are welcome to take colored pencils in. Okay, as long as you don't have all your notes written on the side of the colored pencil. I don't think, I don't know, I wouldn't be surprised if somebody went in that trouble. Okay. But you could have a picture that looks something like this. I have to draw it pretty small. But you could have this picture and this one. And then you could say, okay, we go over here and we move over 2 units. So now this rectangle goes over here. Okay. And then I don't have room to do another one, but then you go ahead and draw it up here. I think you understand what I mean. So 3 pictures would do it without a lot of stuff overlapping. And because of the randomization of these problems, it might get one that doesn't overlap, but you wouldn't necessarily expect that. Okay. Fair enough. Okay. Let's see how we're doing here. Okay. Now I guess a couple of questions can be answered. Well, actually, okay, we've got another one on the axis of symmetry and vertex and so forth. And if you do this one, I think, pretty quickly. No, you'll understand every bit of what I'm saying, and if you don't, I'll give you all the information I can. Okay. So we got the graph of axis of symmetry, vertex, intercept for y equals, or is it g of x equals 3x squared minus 4x minus 5. Okay, well, I would start out with the quadratic formula because it gives you most of what you need. Okay. Find the zeros. X equals the negative of -4, plus or minus -4 squared. And AC is that, it's going to be plus 60, all divided by 2 times 3. You know how to plug into the quadratic formula. Now, what you want to recognize immediately when you write down the quadratic formula is it right here you have your axis of symmetry. And that is negative b over 2a. So if you want to memorize negative b over 2a, fine. But in case you forget it, right there it is, smiling at you. Okay. Anyhow, then x equals 4 plus or minus the square root of 76 over 6 equals 2/3 plus or minus square root of 19 over 3. And you simplify that, you factor 4 out, you get 4 times 19. Square root of 4 is 2, and 2 divides into 6 2 times. So that's how this one simplifies. And I'd like to see this because it's important for other things you have to do. Although if you then, even from this stage, go to decimal approximation, I might not even penalize unless you make some other minor error. Okay. Everything else is right. I might accept the decimal equivalent after you've written this out. I prefer to see this. If I see this, it can kind of cover another little minor error. All right. So that's you're going to need the approximation. A square root of 19 is roughly 4.3. So that comes out to about plus or minus 0.14. So that would be maybe 0.53 or 0.81. Okay. Give or take a couple of hundreds. If I did this correctly in my head, that ought to be fairly accurate. Okay. So there are the zeros. Now the axis of symmetry. Since I used blue up here, so the axis of symmetry is negative 4 over 6. And of course it's x equals, which is 2/3, which is approximately 0.67. You know what? I mean, I said that's about 1.4, didn't I? Then I added and subtracted 0.14. So that was really kind of careless. I thought those were a little close together, but didn't stop me thinking about it. Okay. So let me redo that approximation. 0.67 plus 1.4 is about 2.167 minus 1.4 is about negative 0.73. Negative 0.7 would probably be better. Anyhow, it's about that. Okay. If this is 0.14, I'd stick with what I have if it is. Okay, so there's your axis of symmetry. So we got, and then the y-intercept. And we've done this many times. If x is 0, these are both 0, and you end up with -5. And then we want to then construct this from the toolkit function. And it's going to be helpful if we first look at the graph. Okay, well, okay. That's the y-intercept. The vertex it's on the axis of symmetry. So x equals 2/3. And y equals G of 2/3, which is approximately equal to what? 2/3 of -4 would be -8/3, and 3 times 4/9 would be 4/3, -8/3, and 4/3 is -4/3. I'm going to take a stab and say that's about -6.3. Okay, so here's the axis of symmetry. Y equals -6.3 here. There's our vertex. Since I like to use the red dot, remind ourselves there's a vertex. And the zeros are going to be at about 2.1. Now, if this is 2/3, that'd be 4/3. And then 6/3 would be 2. So let's say here is x equals 2.1. And then at x equals -0.73. So 2/3 -0.73 would be over about here. Yeah, that's about right. I think I had 2.1 too far over here. It doesn't look symmetric. 2.1 should have been a little closer, or -0.73 should have been a little further. But there we have it, and we can sketch a graph. A nice parabola. What's the y-intercept? It should be -5. Well, this is -6.3. The y-intercept, the way I drew it, is here, and -5 is perfectly plausible. If this is 6.3, this could be about 5. Okay. So it looks like it's worked out. So maybe I did my calculations correctly. You'll have your calculator, so you won't have to worry about that, but check. Make sure everything looks the way it should. Please tell me I didn't make a mistake. Okay, well, this function is y equals AF of x minus h plus k. The vertex is pretty close to 2/3 -6.3. A is the same here as it is here. We recognize this as the coefficient we usually call A when we do the quadratic formula. So it's just going to come over. H is 2/3. K is -6.3. And I'll mix up my labels of H and K. There we've got all the coordinates. Now construct the thing the way we just did last time. You start with your toolkit squaring function. You'll stretch it by a factor of 3, so your 4x4 rectangle becomes a 12x4 rectangle. You won't have to invert it like we did before. And then you're just going to shift it over 2/3 of a unit, down 6.3 units. And it's going to be much like what we did there. And I'm not going to take the time to do that because we want to get through as many of these as we can. Okay, well, we've got time to get through a couple more. The next couple are pretty quick. Okay, I've got a handful of chalk and a piece of paper, which I'm not used to carrying, so I'm all confused. Let me put all that stuff down. Now that's just physically confused. The mental confusion is separate. Okay. So next problem, how many turning points does for this? Okay. You want to be careful. You get a turning point for every linear factor. Excuse me. Yeah, got a question. Okay. So there was a question about something that somebody really wanted me to go over. I'm kind of saving it for the next class. So we use the difference quotient to look at the progression of slopes. And that's something you're going to be really glad you did when and if you take a calculus course. It gives you a lot of insight without having to go through the rigors of calculus. Then when you do it through the rigors of calculus, it'll be hopefully the neurons will fire. Okay, so anyhow, again, linear factors give us zeros. Okay, quadratic factors that can't be equal to zero, and you see that you have quadratic functions that are above or below the x-axis that don't give you zeros. So if this thing didn't give you zeros, you're only going to have 2 zeros, and you wouldn't necessarily have more turning points. Okay, that's a little bit of an unfair question because you can have a turning point above or below the x-axis, but you don't necessarily have that. Okay, and we're not going to get into figuring that one out. Just yes, see. Okay, so first you want to look at the graph. You find the zeros. Because the zeros have a lot to do with turning points. And you have to have, for example, if you've got n turning points, you've got n minus 1 zeros automatically. You might have more, but you can have that many automatically. I think we understand why that is. But how do we solve this equation? Well, this equation is going to be 0 if this is 0, but it's not, it's -7 and it can't be 0. But if this, or this. Okay. So x equals -5, or x equals 5, or x equals 3 plus or minus the square root of 89 over 2. And you can approximate that. That's around 9. 3 and 9 is 12. And 3 minus 9 Wait a minute. Yeah. Okay. And 3 minus 9 is -6, 3 -3. Okay. So you got 4 zeros. Now just any graph with 4 zeros. And well, do that. The thing we're doing with difference quotient shows you this thing doesn't curl around like I tried to make it. Okay. So how many turning points? 1, 2, 3, right? We got a turning point here, we got one here, we got one here. Okay, now what's n? N is degree. Now what I haven't done, and we're not going to do it, if you expand this thing, multiply it all out, you're going to get an x to the 4th. That's the highest power you're going to get. You get an x here, you get an x from this one, and you get an x squared from this one, gives you x to the 4th. And if you don't understand that, expand a couple of these. You'll convince yourself fairly quickly that you just count the number. Well, the maximum power of x that you can get by multiplying all this out, that's the degree, and the number of turning points is at most 1 less than the degree. Can't be more, because for degree 3, you can't have more than 4 zeros, which means not more than 4 x-intercepts. So make sure you understand this. Okay. Now, if you got 5 distinct x-intercepts, then you got to have at least 4 turning points. 1, 2, 3, 4, 5 x-intercepts. So you draw a graph that looks like this. Oh, that's really bad over there. But that's even worse. Okay. So you have 1, 2, 3, 4. Okay. You can't have more than 4. And this is even true if the graph does this. You got 1, 2, 3, 4. Well, wait a minute. Actually, I lied. That's 4 distinct x-intercepts, but they all have multiplicity 2. So I need to rephrase that. Of multiplicity 1. So if that didn't have the caveat, they have multiplicity 1, you could just draw this graph and say, ha, you're wrong. It can have 9. Count, 1, 2, 3, what? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Because the degree would be 10. These would all be of multiplicity 2. Should have an x squared involved with each of these. You'd have 5 of them, give you x to the 10th power. Okay. Uh-oh. It's about out of time. We are out of time, but I'm going to do one more. Heck, we're not out of time. Please another second. 12:20. Let's see. Actually, we'll save that one. Save that one, expand and analyze. The expand and analyze on this one, this is what I do want to talk about. You got P of X. Okay. Well, find how many x-intercepts, you find the number 0, or you find the zeros. Okay, you can do this. This or this. Now, in this case, you're going to have 4 zeros because here x is going to be -6 plus or minus the square root of 36 and 108 is 144. Boy, that comes out nicely. Over 2 times 3 equals 12. 6 minus 12. It's going to be -3 or +1. Okay. Now, usually they're not going to come out even. They're not designed to come out with an exact result. But if I did my arithmetic right, that should be accurate. The point, though, is since you have AC is negative, when you do -4AC, you're going to get a positive here. And B squared minus 4AC, B squared is positive. If 4AC is negative and negative 4AC is positive, then you know you're going to have 2 zeros. Okay, so that's a bit of reasoning that I haven't emphasized a whole lot because I'm emphasizing other things. Anyhow, that's going to be 72 and 16 is 88 over 2 times 2. You have 2 more zeros, and they're not going to be the same as these. So you know you've got, so it could be like so, or it could be upside down, but you don't have a negative on the next to the 4th term, so you know it's up here and up here. Okay. Okay, so need a break. So pick up again in a few minutes. Okay, so what we're looking at is on the homework, one that's labeled .421 extension 01. Okay, so you have P of X, degree 5, and I'm writing this pretty quickly because there's a lot to go over, and I want to give you a video that is pretty comprehensive. Okay, so P of X has degree 5. X-intercepts -10, 0, -11, 0, 6, 0, Y-intercept 0, 2, 37. As usual, I recommend whatever problem you have, if you can draw a graph of it, it's going to clarify the problem for you better than if you don't. Okay, so we have x equals -11. Couple of zeros pretty close together here. At x equals -10. At x equals 6. And a 0 at, or sorry, y-intercept at 0, 237. Then I want you to sketch a graph that satisfies these conditions. You're going to find, I think, any problem of this nature, I think I've set it up so that you don't have all the zeros are not linear. Not all zeros are linear. Okay. So if we start up, we come down through this one, up through this one, we come down through this one, we go down through this one, but we couldn't get back up again. Now you're familiar with that. We've seen that previously. Okay. So you're going to have to turn around at one of these. Okay. You can pick. Well, you can't quite pick because you start up here, you can't turn around at this one unless you also turn around at this one, which means you're going to then have to turn around at this one. And you'll have multiplicity 2 here, multiplicity 2 here, and multiplicity 2 here. If you got 3 multiplicity 2s, that means you're going to have 3x squared, which means you're going to have an x to the 6, and the degree won't be 5. Okay. So the degree is 5, meaning it has to start up at one end and down at the other. But it also has to have 2 zeros of multiplicity 2. Or it could have 0 multiplicity 3. You could get away with that, right? So let's say we want to start down here, we come up through here, we turn around here, we come down here, we turn around here, and that works. Yes. That's one way to sketch this graph. Uh-oh, yeah. Word me for a second. How many turning points you have? 1, 2, 3, 4 turning points. That's consistent with degree 5. Okay. So your zeros are x equals -11 with multiplicity 1. X equals -10 with multiplicity 2. And x equals 6 with multiplicity 2. So as drawn, P of x could be then a times x plus 11 times x plus 10 squared times x minus 6 squared. Because at x equals 10, multiplicity is 2, that means you're going to have a square there. And you see that it behaves near this point like a squaring function, okay? And this one behaves like a squaring function near this point. This one behaves like a linear function very close to this point. So it's linear, quadratic, quadratic, okay? I am recording it. Well, there's your P of x. Then you want to estimate the coordinates of the relative maximum. You got a relative maximum here and one here. Let's pick this one because it's a little easier for me to label. You will see it better. if this relative maximum, if this is -10, then -5 would be about here. I'd say about -2. Oh, sorry. X equals maybe -2. I think it's more like 2.5, but I don't want to use fractions. Okay. And then your relative mass, if this is 237, what's this? I'd say this is y approximately equal to 260. The relative mass estimated is -260. Now, for the first time, okay, we use our function. We haven't quite found the formula for P of X. Okay. If X equals 0, that's the y-intercept. P of 0 equals 237, which also equals A times 0 plus 11 times 0 plus 10 squared times 0 minus 6 squared, which is A times 11 times 100 is 1100, and 36 is 396,000. I think 1100. No, I think it's 39,600. Again, doing my little calculations pretty quickly. And it follows that A, since A times 39,600 is equal to 237. A is 237 over 39,600. That's approximately 0.006. Now that's just a familiar way that we evaluate A and so forth. Okay. If my numbers are wrong, you can fix it. So anyhow, with that, yeah. If X is approximately 0.006 times X plus 11 times X minus X plus 11, X plus 10 squared times X minus 6. Okay. Now, the point 0.1 units to the left and 0.1 units to the right of the relative maximum. X would equal -2 minus 0.01 equals -2.01. Zero 1 units to the right, X would be -1.99. Now, this is where you need a calculator, and I can't really do this very quickly in my head. Okay, numbers are just too hard, too much to keep track of, too hard to approximate. Suppose P of -2.01 equals what? Well, first of all, what's P of -2? Well, if x is -2, you've got 9. You've got 8 squared, so that's 9 times 64, which is 540, 594, I think. And 8 squared, another 64, 500 is about 30,000. Okay. And then that's times 0.006. Too far off from 260. About 180. So I'm just going to pretend, and you could calculate this. So this is supposed P of -2.41 equals 178.4. P of -1.99 equals 181.25. Okay. So what does that tell you about the graph? Here's your vertex. Let's suppose that P of 0 was 180. Because actually it's probably closer to 240 or something like that. 237 is too far off. And it's not P of 0, it's P of -2, sorry. Might be a little confusing right now. I'll try to clarify in a second. Okay, this gives us a picture. Here's the point. -2, 180. Estimated max. So I can draw the vertical line that I like to draw. This is x equals -2. And this is the line y equals 180. Then we have the point -2.01. Then y equals 178.43. And then it was a little higher. We have the line where x equals -1.99. Make sure I got that negative sign there. And this line would be y equals 181.25. This picture should make it clear what's going on. So let's think about where we are. We estimated the relative max to be at -2, 260. That's just an estimate from our graph. We don't know how accurate it is. We don't know how accurate we made our graph. So we're kind of estimating that that takes place when x equals -2. Then we check it. We find P of -2 to be about 180. I actually think it's probably much closer to 237 than that. It's based on mental calculations. So let's just say we found this. Let's just suppose this is not what you would find on your calculator. You would find a number here, and you'd use this number just as I've used this number. You would say, okay, if P of -2 is 180, then you have the point -2, 180 on the graph. Meaning that my estimate was a little bit high. Okay, I estimated 260. as I say, the number probably comes out closer to 260 than 180. Then what? We say take the 0.01 units to the left of the relative maximum. What's that mean? That means your x value is going to be 0.01 units to the left. So if x is -2, well, there it is. -2 minus 0.01 is -2.01. 0.01 units to the right is that x equals -1.99. So now we have three points. We can calculate the slopes. So we could do a fundamental triangle here. Calculate a slope. We could do a fundamental triangle here and calculate a slope. We have all the coordinates we need. The run of each of these triangles, to go from left to right, is going to be 0.01. The rise from 178.43 to 180 is 1.57. Which is 151. Slope to the right is 1.25 over 0.01 equals 125. Now that's all easy to calculate, just hard to understand the directions, okay? So you just keep your wits about you, do what the directions say, and you end up with two slopes around this thing that was supposed to be a relative maximum. Now, in the first place, does this picture show you that this is a relative maximum? No, if it's a relative maximum, your slope to the left should be positive and your slope to the right should be negative, shouldn't it? Okay, well, think about it. If you got a relative maximum, then you take some point close by to the left, some point close by to the right, and you got a triangle here, and you got a triangle here. This slope is positive. This slope is negative. Okay. So one thing you see is that the slopes are not consistent with this actually being your relative maximum. It's almost certain that whatever estimate you make is going to be either to the left or the right of the actual relative maximum. Okay. So we've taken the information, we've gotten the formula, we know how to do that. If you do that much, you've got substantial credit. If you can move further, then you get more credit. Okay. We get the formula for the function. We calculate to the left, we calculate to the right. We get a point to the left, we get a point to the right, and we got the point that we get for the relative maximum. Well, that's an important picture. Now, y'all look as a class about like my advanced mathematical analysis class in graduate school, where the professor went off onto all kinds of tangents, okay? And nobody understood what he was saying. He was going too fast for us. And, it wasn't just dumb people like me. There were smart people in there couldn't follow it either, okay? He was a great guy. He was one of my big supporters. So we really liked the guy, but we just looked at each other. going on here? Okay. So I'm seeing a little bit of that. Some of you are seeing more of it than others. It's worth thinking about this. Okay. If you just follow the instructions, it comes out pretty easy. Okay. I'm not going to say any more about that. Except actually, I didn't ask you to find two slopes here. I just asked you to find the slope from here to here. I did a little more than I asked. So I'm not going to ask for both slopes. But what you see from both slopes is the slope is decreasing. What's that tell you? That tells you you're to the left of the relative maximum, because what's happening to the slope of this thing as you move toward the relative maximum? Bigger slope here, less slope here, less slope there. Okay, well worth thinking about, especially if there's a calculus course in your future. Now, excuse me for a second. Those are kind of tripping me up. Okay, I can get to this one now. I want to write over here so I don't block the board as much. I'm going to flip this board. Here's one over. Here we go a little further. Okay. And this would be the 521. So this is on version 96, the first version of the practice problems I sent you. Okay. This says P of X equals X cubed plus X squared minus 10X plus 8 has a 0 at X equals -1. Now, I'm going to say you ought to check this to make sure it's true. P of -1 equals -1 plus 1 minus 10 plus 8. It's plus 10. So, oh, looks like it says X equals -1. I wrote X equals -1, then I used X equals 1. Let's try again. It's going to be -1 cubed is -1. -1 squared is 1. I checked these. Looks like this isn't 0 when X equals 1. Okay, well, what you do if that happens? Then phi of X should be divisible by X plus 1. Okay. So we just divide phi of X by X plus 1. And we get X squared. And we remind ourselves to subtract. And we get -10X plus 8. We get zeros here. And we get then -10. We get -10X minus 10. That's going to be added. That's going to be added. And we get a remainder of 18. remainder implies that this wasn't a zero. Okay. Now, you can say that. You can say, okay, you lied. That wasn't a zero. That's full credit. Just recognize you got a non-zero remainder, so it wasn't a zero. If it works out that it really is a quadratic up here with no remainder, then you just find the zeros of the quadratic. Just set the quadratic equal to zero, and you've got it. Okay. Now, a question that everybody in the last class, I won't name anybody because we're on, but should be proud. A question on the practice test, much like number 723 here. Okay. So I'm not going to do 723. I'm going to go over to the practice test and do that one. And I'm going to go to the first practice test and see first if I can actually, I don't see a problem that's a whole lot like that one. So I'm going to do both of them. You want to see the use of the difference quotient. First of all, how many remember what the difference quotient is? You did it for homework. There are only a couple of problems, so I better remind you. Simple enough. Make sure. Okay. One way or another, you need to remember what the difference quotient is. Now, I might actually, I didn't, so I don't know if I'm doing. Okay, I'm not going to say that. Maybe I won't. Okay, let's do 721. I think it's version 97 because I used the last one. Let's make sure. Let's see if I just versions of this. Did I leave the practice test early? Yes, I did. Okay, actually, there's, I guess, only one version of the practice test. Let me make sure I'm saying it right. I'm getting the practice test and the homework problems all mixed up. Okay. I believe this is practice test version 1. Anyhow. P of x equals this. And we want the difference quotient. On the interval 3.2. Okay, so what's that mean? Well, we can kind of sketch a rough graph. We got x equals -5, x equals -4, and x equals -2. That's where our x-intercepts are. Our y-intercept is 2 times 4, 5 is 40. So here we have this. The long run behavior is down here and up here. So it's just boom, 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 boom. We just come up through here, down through here, up through here, and then we just head on. Now, where's the interval? 3.2. Well, that interval's way out here. The graph is going to be way too high for me to reach. So what we're going to do is squash the graph way down. First of all, if x equals 3.2, if x equals 3, we've got 5 times 7, which is 35, times 5, which is 165. So 165 is out of reach. But we can still say, okay, yeah, you know what? Yeah, I had you do the assignment about 3 weeks ago. We don't even want to have an x and a y axis here. Okay. The interval 3.2. Here's the line x equals 3. Here's the line x equals 3.2. This thing being so far out of reach on any reasonable graph of the function, I'm just going to go up there and magnify things. Okay. So I have these two lines, but now they're this far apart, so I can label things. Okay. Now, if x equals 3, I find that y is 165. Now, if x is 3.2, that's a little harder. Let me try to estimate it. 5.2 times 7.2. 5.2 times 7 would be about 37, times 7.2 would be about, I'll just say 40. And then times 7.2 would be 280, 288. Okay. So now these 2 points will be on the graph. So the graph is going to go through these points pretty close to a straight line. Of course, when you magnify any little segment of this thing, no matter how much it's curving, if you look at a small enough segment, it looks straight, just like the Earth is round. But when you look at it, it looks like it rises pretty level, unless you go up pretty high. Okay. Okay. So this point is on the graph. I think that's accurate. And this is 3.2, 288. Now, it doesn't tell you to do that. It tells you evaluate the difference quotient. Okay. Difference quotient is the slope between the 2 points. So you want to remember that. Okay. The difference quotient is the slope between the points. There's a formula for it that I'll write down, but we don't really need it. Okay. So it says a difference quotient on an interval You just calculate the slope on that interval. How do you calculate the slope? You figure out the coordinates of the 2 points at the left end of the interval and the right hand of the interval. And you find the slope. So it looks like the run is 0.2, right? 3 to 3.2. And the rise is approximately this, because these are all approximations. But this is going to be about 133. 23. Okay, so the slope is approximately equal to the rise 123 divided by the run 0.2, which is about 615. And I'll write a 615 down here so that my picture clearly shows how I got the rise, the run, and the slope. Okay, well, that's not difficult if you know what the terminology means. Now, there's a formula for the difference quotient that I'll talk about next time I use it. The other thing you can do with this now, that's very much like what the last problem on the homework. This is the second page. Okay. Last problem in version 96 of the homework. Yeah, 96 and 97. 96. Okay. It's very similar. I don't want to draw another graph. So I'm going to say it's much like also, I labeled this saying that this is on the practice test. I'm all confused. This is on the homework. Why I couldn't find a version. Okay, so let's consider what happens now if we move further to the right. Could we do a difference quotient on some interval to the right of this? Okay, if we do, it's going to give us an indication whether things get steeper or not, isn't it? If we get a bigger number for the slope, that means it's getting steeper. Now, it's kind of an important type thing. Okay, if you have calculus in your future, being a pre-calculus course, I chose to lay this on you. Okay. There's other stuff that I didn't lay on you because I laid this on you. So you can be grateful, but you probably don't feel that way. Okay, so here we are. So let's choose some interval to the right. Okay, I just set up, let's do it again. Find the difference quotient on this interval for this function. Now, you all chose this interval. It's a reasonable interval to choose. Okay, it's not too far to the right, so the numbers aren't going to get too ridiculous, but they're going to get pretty big. Okay, so if x equals 5, we got 7 times 9, which is 63, times 12. Okay, 60 times 12, 723 times 12 is 36. You get 756. That one's easy to calculate mentally, and I think it's maybe right. So we know that we're gonna have y equals 756. Now, this number's a lot bigger than these numbers, because this thing's going up really fast. Okay, then we have x equals 5 here. Now, here's where I'm gonna have a little trouble, but coming up with a reasonably good approximation. But, okay, so now if x is 5.7, we've got 7.7 times 9.7. Well, that's a lot like 8 times 10, but less. 80, I'm going to say that's about 73. And then we multiply that, I don't know if that's right. Then we multiply that by 10.7, which would be 730 plus about 50, 780. It's not x equals 6, x equals 5.7, and that can't be right. Again, it was 8 times 10, that'd be 80, times 11 would be 880. Maybe I messed up these. That's just not working out. Could be my estimate of 288 inside. I don't want to puzzle over this too long. But interpolating between, again, let's make sure 8 times 10 is 80 times 11 is 800. 7 times 9 is 600 times. 7 times 9 is 63. I use 12 here instead of 10. So that was easy to calculate if that had been a 12, but it wasn't. 630. X up here, y would be approximately 800. But that's not good. I don't want to take a lot of time to correct my own arithmetic. I'm going to say, take just a little bit. 5 times 7 is 35, times 8 is 165. 35, yeah, times 8 is 280. Okay, I'm going to stop here. This, I think, should be 5 times 735 times 8, 280. I get 288 here. These numbers are messed up. So are these numbers. Okay, I'm not going to recalculate them. I'm just going to say, okay. You got to calculate your slope curve and put it in the box. And you're going to find that this slope is bigger than this one. Okay. Now, correctly calculated. Second slope should be greater than the first slope. Okay, my head went haywire on some of this. Too bad because I got easy calculations. They're not right. Okay. Well, without further ado, do you understand? Do you see how this would be calculated? And you see that it's really pretty simple. Just use your calculator instead of your fat head like I did. My fat head, here's our fat head. Okay. Okay. And apologize for the mental lapse apparently. Let's pause for a second, see what to do next. Okay, so I messed up for sure this number, very possibly this one and these. I think some of them are probably pretty close, but I know that one's way off. And what we're establishing here is if we move to the right, this thing keeps getting steeper and steeper. It's not the way the numbers came out when I did it, but that's the way the numbers should come out. Then I just made a couple of notes. What's the difference quotient? It's the slope between the 2 points. The slope on an interval is slope you get if you take the 2 points at the endpoints of the interval. If the interval's from 3 to 3.2, evaluate the function here and get a point. Evaluate the function here and get a point. Okay. Then you have a rise and a run between those 2 points and you calculate the slope. That's all there is to it. Over here, well, same thing. At the intervals from 5 to 5.7, so we got different numbers. Numbers were bigger, and the slope is actually going to be bigger between here and here. Okay, so that's not my mental calculations. I think mainly this one. And then I say we can use the difference quotient to probe the rates of change for the slopes of a function. Now that's a big deal because difference quotients correspond to the derivative in calculus, and it's extraordinarily important. So I want you to get the idea that you want to look at how the slopes behave. And you have the difference quotient that allows you to do that. How would we do it for it? Okay. Difference quotient that you saw in your homework. You remember seeing something like this? That looked somewhat familiar? That's the difference quotient. Okay, you know what this is? Here's x plus h. Here's the point you get. When you evaluate your function at x. The y is going to be f of x. Here's x plus h. X coordinates x plus h. What's the y coordinate? Plug x plus h into your function and you get the y coordinate. Okay. So you have these 2 points. Now what's the slope between these 2 points? Draw a fundamental triangle between the points. Okay. Now see if you can tell me. I'll stop the video for just a second. Yeah, what's the run? Compared to here, the run is x plus h minus x, which is just h. What's the rise? Well, can somebody else tell me what the rise is? Yep. Okay, good teamwork there. Somebody said f of x plus h, and I said there's more, and somebody said minus f of x. Okay. 2 thumbs up. Good teamwork. Okay, so we have f of x plus h minus f of x. You subtract the y coordinates. Now, I want you to understand that I stress these fundamental triangles because it's really important to understand these if you get into a calculus course where you really need to understand them, some calculus courses you do. Any reasonably rigorous calculus course is very important. Okay. So slope, which is the average rate of change, equals rise over run equals what? F of x plus h minus f of x over h. So as I said before, difference quotient is just a slope. Okay. Now you do more with it in calculus after you learn to do limits and stuff, but that's going to be fairly easy if you understand what it means in the first place. Can make a point. Okay. So you have this polynomial, and this is 621 on practice test 1. I've changed the +5 on that practice test to -5 to make a point, as my note says. Okay. Now, first of all, expand. Multiply it out. Maybe what you get is -6x to the 4th. I'm pretty sure of that. And then you're going to get a -6x cubed here and a -14x cubed here. That's -20x cubed. And then you're going to get a -15x squared and a +18x squared. So get 3x squared. And I'm not doing this using the distributive law explicitly, but you've seen me do that many times. That's the way you really want to do it. I'm shortcutting it, which means I'm probably going to make a mistake. Okay, anyhow, -9 times -2x is 18x. And 7x times -5 is -35x. So I think I get -53x plus 45. Okay. Now you can do that in whatever way, but show me the steps if you do. So I asked you to expand it. And then I said, okay, now determine how many x-intercepts. Well, you would naturally then write down maybe 6x to the 4th minus 20x cubed plus 3x squared minus 53x plus 45 equals 0. You might do that, okay? Because I just asked you to expand it, you think, okay, I should use the expanded form. But we don't want to use the expanded form to find the zeros. That's one of the points. I kind of gave you a little misleading instruction. First, I want to see expanded. I want you to see the expansion and the factored form give you the same thing. Okay. So or use the factored form. They're both the same if I expanded it correctly. Okay. Okay. This is preferred. Got a choice. We'll choose to use the factored form because this equation splits into the equation 3x squared plus 7x minus 9 equals 0. Or the equation -2x squared minus 2x minus 5 equals 0. Well, here, X is going to be 49 plus or minus the square root of, it'll be 49, 2708, 157 over 2 times 3. So that's going to be approximately, that's about 12 and a half. It's about 61 and a half divided by 6. It's about 10.2 or negative 2.1 question mark in those in my head. And I think that might be right. No, it's not right. It'd be minus, oh man, that actually comes out. Okay. Yeah, I think that comes out negative 36. Well, that equals 2 plus or minus 6 pi over 4. If I did that right. It's not real. It means there's no x-intercept from this factor. Now, you know that if you have a 4th degree polynomial, you expect up to 4 x-intercepts, right? And up to 3 turning points. Doesn't mean that you have 4 x-intercepts, because the polynomial could factor into this quadratic term doesn't give you any x-intercept because you don't get real solutions. You only get complex solutions, okay? There's an imaginary part to the solution, so it's not going to appear as a 0 on the graph. It turns out it could affect turning points. Probably does. But we do have 2 real zeros. So we get this thing turns out to be a degree 4 polynomial with 2 real zeros. And you can then use that information to help graph it.